Alright, so in this video, we're going to be looking at Atwood's machines. Atwood was a scientist who devised these machines, who created these machines to study motion. So let's look at an Atwood's machine. So what is an Atwood's machine? An Atwood's machine is a machine that has a pulley and a string. And it can have, if it's a modified Atwood's machine, it can have another surface, but let's just deal with Atwood's machines for now, and let's not deal with any other surface. So let me draw some sort of a pulley here. Actually, I'll do this in a different color. So this is my pulley. What is a pulley? Well, a pulley is something is an object, is a device that can have a string wrapped around it, and you can essentially move the string around in any direction. So in this direction or in this direction, and it's going to move around based on gravity. So that's essentially an Atwood's machine. So let me draw a string. So this is going to be a string that wraps around this Atwood's machine. And let's say that this string is rigid. Okay, so this string is not weak or anything like that. So it's not going to break. And so this is a typical Atwood's machine. And what we would have here is we'd have some masses attached. So we'd have a mass attached here and a mass attached here, and this would be M1. This would be M2. This could also be M2 and M1. Doesn't matter. But essentially, what we're going to be looking at is this pulley string system is going to move in the direction of one mass. In this case, this is a larger mass based on my drawing, so it's going to go in this direction. It's going to go in this direction. So it's going to be going down, and this is going to be going up. That's pretty intuitive. There's a lot we can study with these Atwood's machines. We typically study forces with these Atwood's machines. So the summation of the force is equal to the mass times the acceleration. We know this formula. This is Newton's second law, right? Newton's second law. We can actually study forces that are acting on this Atwood's machine. Obviously, there's not going to be any applied force, but there is going to be a force that's pretty apparent. That is going to be tension, of course. So let me do this in blue. So tension is going to go up here in the upward direction. Even for this mass M2, it's going to be tension going up like that. And then we're also going to have a down force of gravity, right? So that's just going to be M1G in this case. And in this case, it's going to be M2G. M2G. Okay? So these are the apparent forces that we're going to have. Now, obviously, there could be other forces if we're looking at a modified Atwood's machine. A modified Atwood's machine, we'll be covering this in a future video, but it's something that you have like a table or something like that, and then here you have like a pulley attached. And so this is our pulley, something like this. And a string is attached here, and it's going to have like a mass over here on this table, and there's going to be friction in this case, right, going in this direction. And then there's going to be another mass attached. Okay, so this is an Atwood's machine, a modified Atwood's machine. And in this case, we would have other forces. But in a regular Atwood's machine, we wouldn't have to worry about all these other forces. It's just this, okay? Now, if someone asked us to find the acceleration, what would you do? Well, we would look at the forces, and we'd analyze the forces, and we'd look at the masses and all that. But the thing that you need to know is that you can always solve this problem by treating the whole Atwood's machine as a single system. What do I mean by that? Well, basically, if we look at all the forces, right, and we look at all the forces as system forces, and if we deal with the acceleration as a system, then we'll see that we'll have internal forces, external forces, and forces that we can analyze as a system. So let's see what I mean. So the tension force is always going to be an internal force. It's an internal force that cancels out. So the tension force, this tension and this tension are going to cancel out when you deal with this Atwood's machine as a system. When you deal with it as a system now, there's going to be forces that both of these forces right here, due to gravity, they're going to be analyzed for the entire system. So since this is going to be moving in this direction, I'm gonna set a direction. So I'm gonna set a direction of motion to be positive, and that's gonna be this direction. So this direction is gonna now be positive. That's how I've defined it. You can obviously define this to be negative, but for me, I chose it to be positive. And so here now you have to deal with the forces that are on the system forces that are making this whole thing move. Well, it's going to be M1G, and this is going to be M2G that's counteracting that. Of course, tension, it doesn't matter. So when we look at the summation of the forces, and this is going to be now the system approach, so I'm going to rewrite this formula with the system. So it's going to be a subscript SYS, and then the mass of the system, and then the acceleration of the system. Since this whole system is going to be moving in this direction, the acceleration is going to be the same. Obviously, when we deal with each object separately, we're going to have acceleration that's going to be different, but that's going to be, of course, the signs are going to be different. That's all that's going to be different because of the direction. Anyway, so summation of the forces of the system. So we will see that this is going to be M1G minus M2G, right? Because M1G is in this direction, M2G is in this direction, so the whole system, we have these two forces that are acting. This one's for, this one's against, so we have like M1G minus M2G. And this is going to be equal to mass of the system, well, that's M1 plus M2. Those are the two masses that are on this system, multiplied by the acceleration of the system. The acceleration is going to be, of course, it's a vector quantity, so the acceleration has direction. It's going to accelerate in this direction, so it's going to be, of course, positive. Okay. All right. Okay. So you can also think about this as the magnitude of the acceleration, right? Because this is technically not going to be the acceleration for each object, because one's going to be positive, one's going to be negative. But we can think about this as the acceleration of the system. Now we can divide the M1 and the M1 plus M2 both sides. So M1G minus M2G all over M1 plus M2. And this is going to be equal to the acceleration of the system. Okay, so this is your formula, right? This is what you can think about. Now, I wouldn't recommend memorizing this, because there's no point. You can always think about what I did here, and then that would obviously make sense. Now, what I wanted to do next is I wanted to look at the tension. So let's say that the next part of the question asked you to find the tension acting on an object. You can choose one object. So let's say I'm going to choose mass 1. And we're not going to worry about this anymore, because we're not dealing with the system anymore. So let's deal with this object. So again, summation of the forces is equal to the mass times the acceleration. Mass times the acceleration. So we're dealing with mass 1. And we're going to deal with up as positive and down as negative. So that's typically the notation. That's typically what we use. So tension is going to be positive. So tension minus M1G is equal to, of course, M1, because that's the mass, times the acceleration of the system, because the system acceleration is equal to the mass acceleration. Now, the acceleration, however, in this case, is actually going to be negative, because the acceleration, this is going to be moving in this direction, right? This whole system is going to be moving in this direction. So the acceleration on this mass is going to be a negative acceleration, since it's going down. On this mass, however, it would be accelerating upwards, so the acceleration is going to be positive. So this is going to be negative acceleration of the system, so negative, since this was the magnitude. So let me make some space here. So this is just going to be negative. So if we look at this over here, the tension can just be found by adding M1G. So tension is going to be equal to M1G, let me just do this, negative M1 times the acceleration of the system plus M1G, Tension is this. Okay, now next thing I wanted to do is I wanted to take this acceleration stuff and put it in here, because we can do that. We don't have to, but let's just do that here. So I'm going to take this and move it down here again. Tension is going to be equal to negative m1 times m1g minus m2g all over m1 plus m2, and then plus m1g plus m1g. This is your answer. Hopefully this made sense, how I dealt with this problem here. Basically, Atwoods machines are very interesting machines that you'll see in a physics textbook or some sort of a class. These are Atwoods machines are basically like you have a pulley, you have a string, and you have objects that are attached. You can obviously make Atwoods machines harder and harder by potentially having angles involved. But at the end of the day, if you remember this formula right here and apply it correctly, you should get the right answer, okay? You should get the right answer for that. So make sure you write the signs positive and negative appropriately because you don't want to mess up on that. Of course, I could have wrote this as m1g minus m1 and all of this times all of this. But again, it's the same thing. Make sure you get the signs correct and not mess up on that. And next video, we'll be covering modified Atwoods machine.